presentation at CES 2017. CES is becoming a tradition for Mobileye. I think that this is our 4th year in a row, and the presence continues to build, just like the theme of autonomous driving. So the timing of this conference isn't so great for relaxation over the holidays, but it's great timing to review the accomplishments of the year before and set the technology agenda for the year after. Before introducing Amnon, I just have to read quick forward-looking statements. Today's presentation contains forward-looking statements that should be understood to be predictions based on our current expectations regarding future events. And many factors described in our SEC filings and releases may cause our actual results to differ from any predictions or projections. We ask that you refer to the full disclaimer in our filings. So without further ado, let me introduce Professor Amnon Shashua, Co-Founder, Chairman, and CTO of Mobileye.
Good morning, everyone. I appreciate spending your time coming here. So I'll talk about our progress on autonomous driving, not only about what we are doing in the area, the business status, but also the need for partnerships. It's not only a technological problem, it's a logistical problem, and I'll spend some time on that as well. And I'll also, part of the time, I'll be slightly technical. I'll show some very, very interesting technical stuff, new developments that are really touching upon the core of the problem, reaching autonomous driving somewhere in 2021. So just to remind everyone and the setup, we identify 3 major areas. We call them pillars, technological pillars, that are needed to be addressed fully before we can say we have autonomous driving. The first is the obvious one. It is about sensing. We have sensors around the car, cameras, radars, laser scanners. All the sensing information is fed into high-performance computing for the purpose of understanding our surrounding, building an environmental model of the surrounding. The second, and this part has quite an interesting history going from driving assist. Driving assist is all about sensing, but only forward-facing sensing, so that we have years. The industry has years of experience in understanding sensing in that regard. The other 2 elements are relatively new to the industry. One is about mapping. In order to create the right redundancy, one needs to have very, very detailed maps. These are called high-definition maps, and localize the car inside this map at very, very, very high accuracies, about 10 centimeters accuracy. This is way beyond GPS. And it's not only a technological problem, it's a logistical problem. How do we build the maps? How do we update them such that if there's a change in the environment, it will be reflected in the map within seconds? The way we see it, it's the Achilles heel of the entire industry. And we call this driving policy. Policy is a word coming from robotics. It's a mapping from sensing to action. It is all about how we handle ourselves in busy traffic. This is why we take driving lessons. And the state of the art today is very simplistic driving policy, and I'll show you what needs to be done in order to reach the levels that are required to say that we actually have autonomous driving capabilities. So this is the content. I'll start with a recap of 2016, the accomplishments of 2016, what we expect to see in 2017. Then I'll talk about our mapping, REM, it's the Road Experience Management. I'll update where we are, what kind of alliances we have achieved, and where we're going from there. There has been a lot of progress during 2016 on pushing forward both technologically and business-wise the idea of crowdsourced mapping that I presented last year at CES. Then I'll move into level 3 autonomous driving. Some of it is actually starting this year with Audi, and then I'll talk about other programs. What does it mean at level 3 and where we are at level 3? Then I'll start the technical part of my presentation today about the driving policy, what it is, why is it a problem, why is it the Achilles heel of the entire industry, how we are approaching it, and why there is a need for partnership there as well. And then I'll move to the last part. I'll talk about fully autonomous driving, level 4, level 5 autonomous driving, what kind of partnerships we have achieved, where we are and where we are going in that regard. So I'll start with driving assist. If we look at 2016, to date we have delivered about 15 million IQ chips so far. I think 2016 alone was about 4.5 million chips, but I'm not, don't take my word for the exact number. We have 6 OEM launches during 2016, and you can see that AEB, autonomous emergency braking, is almost in every launch. You can see also the variety of tier 1 partners in these launch and the variety of car manufacturers. In 2016, we also had new program wins, and it was a very, very good year for new program wins. We won 12 design wins, 12 program wins over 11 car manufacturers. Because I'm not at liberty to associate car manufacturer, year of production, and the content, I did it in this way, where we have all the OEMs are listed here. You see here 11, I see here 12, 11 car manufacturers, and these are the 12 programs. You see that AEB is almost in all of them, and all of them are quite advanced in terms of their features. You see here also the variety of tier 1 partners in all of these programs. So 12 program years, 12 program wins during 2016, and this gives us production until 2026. So we have here a 10-year visibility. I'm not talking financial-wise, talking production-wise, 10-year visibility starting from today. If we look at one of the launches in 2017, we have about 6 new launches coming out in 2017. The one that I want to highlight is actually a level 3 autonomous driving by Audi. It's called ZFAS. Audi has presented the ZFAS back in 2015 in a keynote presentation here at the CES. And I would say it's the most sophisticated and ambitious driving assist program coming out in 2017 to date. It's a centralized box. It is multi-sensor, 360-degree sensing. It provides a takeover request of 10 seconds. This is something which is really industry first. It means the car, when it needs you to take control, the driver does not need to take control instantaneously. There is a period of 10 seconds, a grace period of 10 seconds to take control, and this is why it's called level 3. It operates within an envelope of constraints, but within that envelope of constraints, now you have 10 seconds of handoff. It contains our most advanced features of free space, HPP, holistic path planning. All our most advanced features are included in this program. It's running on IQ 3. And it's my pleasure to call on stage Alex Vokotic. Is the Senior Vice President of Audi. He's also the Head of Development of Automated Driving. He'll say, come on Alex, he'll say a few words about ZFAS. It's a pleasure, Alex.
For me, it's an honor to be here with you, Amnon, because first of all, we speak the same language, the language of innovation, the language of driving forward the limits of what we are doing. And we're looking back to a history, being the first to bring a camera-based AEB into market together.
2015, that's right.
And also the ZFAS project that, as you mentioned, is a very unique and far ahead project in the nowadays. You are benchmark for image processing in the community, and even if there's a lot of noise about a lot of technologies that are being used in future, I think that that's the Audi belief to make things safe. We will combine those technologies to achieve the higher levels of safety. And we're looking forward for a really intense partnership and bring things forward.
Thank you,
Thank
Alex.
you for all the work we did together and the achievements we made.
Thank you, Alex.
So,
thank you.
Thank you.
Bye-bye. So, this was 2016. This was ADAS. Now we'll start moving to our mapping. REM is the road experience management we presented back at CES last year. Just a few words of a baseline of setup for those who are not familiar what REM is. It is an approach for mapping. So high definition mapping is a critical ingredient to enable autonomous driving because one needs redundancy. You have redundancy when you're doing object detection because you see the same object through several sensor modalities, through cameras, radar, laser scanners. Every piece of the technology needs to have redundancy. So when you're talking about drivable paths and their semantic meaning, the only sensor that can provide that is the camera, and redundancy for the camera will come from the map. So the map contains the same information about the drivable paths. But in order to use the map, you need to localize yourself very accurately, at an accuracy of 10 centimeters. So there's localization, and there is very high detailed map. And the way the traditional mapping works is there's heavy use of laser scanner equipment, and there's lots of manual work. There are fleets of vehicles driving through a path, collecting three-dimensional information. And then after some partial automated processing, there's lots of manual work in order to create the high-definition map. So it's a big enterprise in creating the high-definition maps. And then there's the issue of how do you update the maps. We want to have instantaneous update. If something is changed in their environment, we would like that change to be reflected in real time or near real time in our maps. And this is very, very difficult to achieve if you are talking about specialized equipment and fleets of vehicles that would be driving. So it's a matter of scaling up. It's cost and then scaling up, which is very challenging in a traditional mapping. What we have presented last year is a crowdsourced idea, which we want to leverage the fact that almost every new car coming out today has already a front-facing camera. And the front-facing camera is very, very sophisticated in terms of its sensing capabilities. There is a lot of AI going on in the camera sensing. So the camera can understand the environment, the front-facing environment, identify landmarks, identify the lanes, and harvest information to create the maps, and also use the landmarks for localization. And because it's crowdsourced, and it's using already equipment that exists in the cars today, we're talking about very, very minimal cost. And cost is very important in this industry, because the motivation for going to autonomous driving must be based on economical value. And cost is fueling economical value. If you have an enterprise in which the cost is not optimal, it may hinder the entire industry. And maps, since maps are critical to achieve autonomous driving, one has to find a way in which these maps are done almost cost-free. And crowdsourcing is a very neat way to do it. Okay. So the general idea is in this picture, we have the cars with our chip inside, sensing the environment, finding landmarks. These is example of landmarks, pavement markings, traffic signs, traffic lights, any billboard, anything that is stationary in the world is a landmark. And then the lane information and the landmarks are sent to the cloud. In the cloud, we have back-end software that pieces everything together, creates a road book, which is a high-definition map, and then it's transmitted back to the cars. Okay, so this is the general idea. So what are the features here? We're leveraging driving assist, so there's no specialized equipment. The cost is minimal because the cameras are already in the car. All what you need is to have additional software and ability to communicate. And we're leveraging crowdsourcing because the bandwidth of the data is very, very small. We're talking about 10 kilobytes per kilometer of transmission, which is very, very small. So if you drive 100 kilometers, it's 1 megabyte. And then automation. The entire process is automatic. From the sensing in the car to the back-end software in the cloud, everything is being pieced automatically. So there's no manual intervention. And then we have the density of the data source. If we have millions of cars already with cameras, then those millions of cars will send information, and then the scaling up becomes very, very natural. Right? So imagine every car has this ability. Every car is enabled to send data. We can map and update the map almost instantaneously. So what REM introduces is a highly scalable and creates a high-definition map, a live high-definition map, and at very, very low cost. The only cost that is necessary here is the cost of communicating 10 kilobytes per kilometer. Okay, and here's kind of a table of what are the pros and cons compared to the traditional mapping. So we have scalability and cost and time to reflect reality. That means if the environment changes, we would like the map to reflect that change instantaneously, and this is kind of diametric opposite to the traditional mapping. Scalability is a problem because you're using specialized equipment, fleets. Cost is high, again, for the same reasons, and the time to reflect reality suffers because, again, it's specialized equipment and fleets of vehicles. Traditional mapping, you need a single ride through every path. It's sufficient. In our case, you need multiple rides through every path because, again, we're relying on crowdsourcing. So every path is driven by many, many, many cars. We reach the accuracy of 10 centimeters with 9 rides per path. Maybe in the future we can reduce that a bit, but we need multiple rides through every path. And we require collaboration among car manufacturers because not a single car manufacturer can create enough density in order to scale this up. And this is also a logistical problem that we need to address. Okay, and so I'm sure that you heard there is a demo vehicle in the cooperation of Delphi and Mobileye. It has a 6-mile route, highway and city traffic. And REM is used in part of the way, in most of the way, to activate the autonomous driving. So we sent car driven a number of times through the route and then automatically created the map. And then the Delphi car online does the localization and uses the map to create a redundancy and control the car. What I'm going to show here is part of this route. These lines are a projection of the map onto Google Earth. So this gives you a sense also of accuracy because if it's not accurate, the line would not sit on the lanes. So it gives you a sense of kind of few tens of centimeters of accuracy. This is the projection of the map into the video. So again, it also gives you a sense of accuracy because if it's not accurate, the projected line will not sit on the lane mark. Okay. So let's run this, and you can see it's a projection. For example, this line has a very forward-looking distance. The colors, this is a road edge. These are the lanes. This is the center of the path, and you can see this also back in Google Earth, also in city traffic. And these are the landmarks you can see here. And the point here, all of this was created automatically. There wasn't a single manual intervention. Multiple drives take this data into a computer. Everything is created automatically, and this is used live in the Delphi Mobileye demonstration. And it's a very neat demonstration. I'll show later in my presentation some live clips from the demonstration. Okay, so this is the first use of REM in actual driving that is available to the public to see. Okay. So now, what is the business status? I talked about the idea, about the technology. So first we have the REM harvesting. Cars with the software on the IQ chip that with the communication capability to send it to the cloud. We have already commitments for 2018 for about 2 million cars from 2018 to be sending data. Okay? And 2 million is a nice number. It's not 70 million, the number of cars produced annually, but 2 million is quite a nice number. It allows us to start building the maps globally, not only in one local area, but globally. This is one thing. Second, we have signed a strategic partnership with HERE. We announced that last week. And of course, this is the context of sufficient progress we have with the consortium partners, with BMW and with Volkswagen, and Audi is part of the Volkswagen group in this regard. And we're talking about HERE using our technology to update their high definition, their live HD map using our roadbook, the map that is being created on the cloud, and also the pieces, the fragments of data used to create the map. All of this would be available to HERE. Our roadbook would be a layer inside HERE HD map, and HERE would productize our roadbook. And we'll also be using infrastructure from HERE for data ingestion. It's called OLP. their open location platforms. And also we will explore additional verticals, not only automotive verticals, to try to commercialize, monetize this joint asset. Another cooperation we have is with Zenrin, the Japanese map maker. This is not for harvesting, this is for creating an HD map of Japan. So it would be available 2018 with an Asian OEM who would be introducing a level 3 a car, which can give you complete autonomous driving under all situations on highways, and the high definition map is required. So by October 2018, all of Japan highways would be mapped using a combination of REM technology and Zenrin's technology to create a high definition map. And after October 2018, there will be also data being sent as crowdsourced from those vehicles and other vehicles from that car manufacturer. So it's a three-way relationship between Mobileye, Zenrin, and the OEM, and maps would be ready, not built, ready October 2018, and by 2020, entire Japan, everything in Japan, all city roads everywhere in Japan. So this is another a very important relationship. Then we are working on creating an industry collaboration, creating, rather than having specific relationships with every OEM separately, we would like to create a global, a worldwide HD map, a worldwide roadbook by mixing data from all car manufacturers who would agree to join. And I think that this is key to reducing cost and creating a standard that everyone can use and enable autonomous driving and enable the economical value of autonomous driving. So because again, the maps is not only a technological problem, it's a logistical problem. And one has to appreciate the dimension of the logistical problem here. And yeah, this is what here, we'll get the scalability. So what we're working, there's an ongoing negotiation for a world HD map, which is very, very advanced. Hopefully it will be concluded very, very soon. It's all the elements of data flow, rights of use, data ownership, the mixing of data from multiple OEMs, the financial model, all have been agreed. It's just a bit of legalistic stuff that needs to be taken for such an important contract that is being made, and it's being made with multiple car manufacturers simultaneously. And I believe that once this is consummated, it will become an industry turning point. This would be an industry-wide collaboration, and into that, additional car manufacturers hopefully would join, and will create kind of a world HD map, all crowdsourced, using ADAS as the building block to do that. Okay. So why is REM so important? First, it's a game-changing way to create and update HD maps. The cost is minimal. Then the only cost you have here is sending data to the cloud, and this data is very, very low bandwidth. It's being adopted by major map makers, already mentioned here, and Zenrin. So the map makers are our customers, are not our competitors. This is very, very important to emphasize. We have already commitment for about 2 million vehicles starting 2018 that will harvest, that will start sending data to our cloud. HD mapping of Japan by 2018 in cooperation with Zenrin, and negotiations with car manufacturers on World Roadbook is ongoing. So REM is an enabler for both low cost and high scalability to support level 3 up to level 5 autonomous driving. This is why it is so important. I'll move now to talking about level 3 autonomous driving, where we are, and all our partnerships or car manufacturers that we are working in production towards to. So when we talk about level 3, we're talking about highway-only capabilities. The takeover request, it's not instantaneous. As I mentioned, with the Audi Z-Fast, it's about 10 seconds. And the high-definition map is required. Those are the three functional elements that distinguish level 3 from anything else, from ADAS and from level 4, level 5. In terms of the sensing, the way the sensing is being done, typical sensor configuration is the camera is only forward facing. We have either a trifocal, you see here, 150 degrees, 52 degrees, and 28 degrees, kind of a three cameras, or it is a ultra high resolution camera with a 120 degrees, and it's a 7.4 megapixel camera that would be out in 2019 production programs. And if we go back to here, there is a radar cocoon. So this is kind of a graphic way to explain that there's a radar cocoon. So we have 360-degree radar sensing, and normally we have a front-facing LiDAR, about 145 degrees laser scanning front-facing. This is typical. There are changes. Not all car manufacturers have exactly this configuration, but this is the typical configuration. And the redundancy among sensors. So most of the redundancy is front-facing, and typically there are 3 layers of redundancy. You have camera front-facing, you have radar front-facing, and you have a laser scanner front-facing. You have a rear-facing camera in some of our models in order to create redundant lane sensing from the rear and from front-facing. And there is no redundancy for the full 360 degree. So most of the redundancy is forward and back. Because we are in a highway situation, it's less complicated than in city driving. If we look at the programs that we have, we mentioned Audi 2017 that's coming out. And again, I did this trick, instead of stating which car manufacturer, which year, these are the car manufacturers that we have production programs, and these are the years, so 2018, 2019, 2021. So 2021, of course, has been already advertised. This is BMW. So BMW is coming out with 2 programs, level 3 and level 4. Right? It's 2 programs that are coming out, 2021. And you can see that 2 out of these 5 have already REM commitment into the program. Okay. So this is where we have 5 production programs going on level 3 autonomous driving. Now let's go into the technical part of this talk, into driving policy. When we look at driving policy, I put here a slide. I put the same slide, I think, last year. It's a common theme. It's nothing to do with Google. Google is very, very capable company. Nothing to do with Google itself. What this article talks about is that the autonomous cars that we see today are very, very defensive. They follow the rules to the letter, very, very slow, very defensive, and it's a problem because you can't merge into traffic when you're driving like this. And when we look at driving is a multi-agent game. It's not only we sense the world and we decide what to do. The world also, the environment also reacts to what we're doing, and we need to negotiate. So as long as the other agents are human, the robotic agents, they should adopt a human-like negotiation skills in order to merge into traffic. But on the other hand, you need to guarantee safety. Society will not accept fatalities or a large number of fatalities due to robotic cars. Even though humans are involved in large number of fatalities, robotic cars, society will not accept robotic cars to be involved in many fatalities. So we have to guarantee safety. And how do we how do we combine both human level skills in negotiation yet guarantee safety is a challenge. So to be concrete, I'm going to introduce one of the maneuvers which is found in most of the negotiations that we experience when we are driving. It's called the double lane merge. The double lane merge, if you look at this clip here, is when cars come from 2 sides and so the red cars, they want to go left, and the blue cars, they want to go right. And when the road is busy, right, there could be lots of deadlocks, because in order to complete this, squeezing in is not sufficient, because you may interfere with the plans of the other car. It's not that the other car just simply needs to slow down to allow you to squeeze in. The other car may have other plans. The other car may want to move to the other lane as well. Another thing that is unique about the double merge is that there is, people usually talk about the 4-way stop as the most complicated negotiation maneuver. Actually, it's one of the easiest maneuvers, because there are rules. There is right of way, so what you need is simply right of way and squeeze in. In the double merge, there are no rules. You're simply supposed to drive safely, don't create accidents, and negotiate. And you need to plan many seconds ahead, because when the road is busy and you have 100-meter stretch in order to move to the other side, you need to plan. You need to plan not just 1 second ahead, you need to plan 5, 10 seconds ahead. And planning is computing, and this could create a big bottleneck in computing. And heuristics would create a very simplistic policy, would create a very simplistic driving policy. So this is one of the most complicated maneuvers, and I want to focus on that. Okay, so let's look at 2 examples that are on my way to work. Now, this is Jerusalem, just to give you an idea. Driving in Israel is like driving in Boston. So I lived 5 years in Boston, and I felt at home from day one. It's very similar. You know, Israelis mostly drive not to get from point A to point B, is to sharpen their negotiation skills. Okay, so so let me show you. So the point here is double merge. It's not a roundabout, and let's look at this double merge. So let's focus here. So you see cars are coming from 2 lanes. Some of them are going to continue. Some of them are going to go to this part. So this is kind of normal, just to get a sense of idea of double merge. And now let's look at this car. He's going to go from here to here. He has to slow down. The other is causing the other cars to slow down, and he's gradually going here. Okay. Now let's look at a more interesting case, and this case happens. It's not. Yeah. It's not rare. Okay. So what we do, right? Our negotiation is not negotiation by talking to each other. It's negotiation by motion. My motion signals to the other drivers my intention. Whom do I want to give way? Whom do I want to take way? And these negotiations are kind of complicated. Let's look at this one here. So I'm putting this car, busy traffic. Okay. This one is not going to succeed. So this is an example of negotiations that do not succeed. Okay, so it's trying. Nobody's going to let him get in. Okay. Okay, and we're fast forwarding everything here, right? You see, it's fast forwarding. So you can imagine this planning ahead. How much time needs to plan ahead? This one here is having a hard life. He's long. Nobody wants to let him in. Even this bus here, you know, even he's long as well. He doesn't want him to get in. All right. And again, we're fast forwarding this, and eventually he got in, and this one. Okay. Let's look at the last one. Right. Again, so you can appreciate the complexity going on here, and you can clearly understand that, you know, autonomous driving today, what you see today, is far away from what you see here, right? And we know that. We know that because there are test vehicles out there by Uber, by Google, even now by us, Delphi, and Mobileye. And reporters sit in the car and report back. You know, they all report of simplistic type of negotiation. Whenever something complicated happens, the driver behind the steering wheel takes control. Right? I would say that this is the Achilles heel of the entire industry. It's not sensing. Mapping would be handled eventually, and I think the crowdsourcing is the way to handle it. It is its driving policy. We need to endow the robotic cars with human-level skills, yet guarantee safety at the same time, and we need to be able to handle these kinds of situations. Okay, so what I'm now moving towards is that we need machine learning. Now, when you look at driving policy today, the kind of traditional driving policy doesn't include machine learning. It is more dynamic programming, brute force, kind of you expand, you open a tree by looking at all possibilities, and it grows exponentially with the number of agents and the number of time that you need to plan ahead. Now, why machine learning? It's a tricky question, because it's obviously, okay, let's use machine learning. But there is a reason why people don't use machine learning for this, and the reason is due to safety. So let's first understand why we want machine learning, because there are many possible scenarios. And the rule-based approach, or a brute face, pruning all possibilities, you know, will likely, because it will explode computationally, would likely yield a very simplistic policy. And this is the kind of simplistic policies that we see today. It's a multi-agent game. We need to understand intentions of other agents, what they're about to do. There's a spectrum between defensive and aggressive trade-off. And this point on the spectrum is location-based, right? As we said, people in Boston drive differently from people in California and so forth, right? So it's not that there is just follow the rules. There is a norm, there's a conduct, there is rules of breaking the rules that we need to learn, and this is location-based, right? And then we have all this negotiation. We signal intention through motion. We need to balance safety guarantees in all of this, and to balance norms, rules, defensive-aggressive trade-off while guaranteeing safety. Okay, and then we have uncertainty, right? Everything has uncertainty, sensing has uncertainty, and we need to put uncertainty inside our sensing state in general. Okay, so we say, okay, obviously, let's use machine learning. So there is a problem here of using machine learning. And when you look at machine learning, what is machine learning? You want to learn by observing data rather than by programming by rules. This is a machine learning. There are many aspects in which programming by rules becomes unwieldy, becomes too complicated. And image recognition, object detection and image recognition is a good example. If you try to program by rules what constitutes a human face, it becomes very, very difficult to achieve high quality detection. But if you observe by data, you can get much better performance. So what are the advantages? It's much easier to observe and collect data than to figure out what are the rules behind the problem that you want to solve. The downside, the dark side of this, is that machine learning is based on the statistics of data that you feed, and the way we optimize, the optimization is done stochastically. It's called stochastic gradient descent. So we sample the data. So we need to cover all the corner cases, and covering all the corner cases is kind of a problem in machine learning, and this is why it takes a long time to mature a machine learning algorithm, especially in the automotive area. So we have corner cases, and we can fail on corner cases because we are based on observing data. Okay, so what's the problem here? So there are corner cases, there's data. There is a problem. There is a problem because there are two, when you look at sensing and you look at driving policy, there is a big distinction between them. When you look at sensing, you're talking about sensing the present. You know, give me a video or image, tell me where all the road users are around me. And the technology for that is deep supervised learning. All what you hear about other presenters talking about AI and so forth, they're talking about deep supervised learning. To do the driving policy, we're planning for the future. Planning for the future is under a field of machine learning in robotics. It's called reinforcement learning. Okay, what's the big deal? So there's reinforcement learning. The big deal is how do you handle data? So let's look at that. When you look at supervised learning, the actions are predictions that you are making do not have an effect on the environment. I look at an image, I see there is a car there. Whether I make a mistake or don't make a mistake doesn't affect the environment. Okay? It means that the data for training and validation can be collected in advance. And when I update my software, I don't need to recollect the data from scratch. I already collected the data. I just need to find all the corner cases from the data and train my algorithms again and again and again, but the data is fixed. I collected the data offline. When I'm talking about reinforcement learning, our actions affect the environment. If I decide now to accelerate, to slow down, to move to the left, I'm affecting the environment. I'm affecting the actions of the other road users. Therefore, the data collection has to be done online. And every time I change my software version, I need to collect the data again because I'm affecting the environment. So now this is a big problem. If I need to find corner cases, and these corner cases are rare, and every time I make a modification of my software, I need to collect the data again, and we're talking about huge amount of data, then it doesn't sound like an attractive proposition. And this is why machine learning is not used for driving policy. Okay? So the question is how do we guarantee safety in a machine learning-based technology? So I'm not going to explain that. We published a paper at NIPS last month showing a way to do that. And let me show you an experiment, a result. And this is, let's go back to the double lane merge. So we have here a simulator in which all the agents were learned by our algorithm. And these agents are placed randomly on the simulator, and now they need to move and do their task. And their task is the red cars needs to move right, the white cars need to move left, And let's look at it again and again. I'm going to show several scenarios here. And we're talking about dense traffic and complicated maneuvers, and all of this is learned through data. There's no brute force or rule-based. Okay. And there are two dimensions. There are three dimensions here. One is safety, and the entire model is based on 0% accident. An accident cannot happen in our model. Second dimension is the probability of executing the maneuver. Because as we saw with humans, they can fail. They can not be able to negotiate and fail the maneuver. So what are the chances of executing the maneuver? And the third dimension is what is the processing time of this? Okay? So when we run this for, say, 100,000 runs, and in each run there are 8 agents placed randomly on the stretch in each trial, we have 0% accident because the model guarantees 0% accidents, and we have 99.8% success. So only 200 trials out of the 100,000 failed. Not failed because there's an accident, failed that not all the red cars moved right and all the white cars moved left. And when I looked at all those 200 cases, I'm not sure that a human can do that. Very, very difficult cases. Because these cars are randomly placed. Sometimes they are placed towards the end of the stretch and you don't have enough time to do the maneuver. The third dimension is processing time. We're talking about 1 millisecond of processing time on an IQ4. So just to give you an idea, let's assume we're running at 10 hertz, 10 frames per second. So 1 millisecond would be 1% of the amount of processing we use for sensing. So the driving policy takes about 1% of the amount of processing we use today for sensing. And this is also a very big breakthrough because the way driving policy is done today is very, very compute intensive because of the brute force, because you are expanding the tree of all possibilities, and your time grows exponentially with the number of agents and the amount of time that you need to plan ahead. And here, because we're using a novel technique in machine learning that we developed, which on one hand guarantees safety, on the other hand can get us a 1 millisecond, 1% of the sensing. So this can run inside our IQ4 without us even feeling it. Okay? And another point here is that we see the driving policy also as a logistical task. It's not only a technological task. A logistical task meaning that cooperation among car manufacturers, among actors, would benefit all because a single actor cannot collect enough data that will cover all the locations of interest for autonomous driving, especially in cities. So every actor that we know today, whether it's Uber, whether it's Delphi Mobileye, whether it's the BMW Intel Mobileye, they're all planning on a small number of cities. Uber is planning Pittsburgh and maybe San Francisco, and Google is Mountain View, Austin, Texas, and so forth. Now, you can't build an economy of autonomous driving if you drive in one city, right? You need to build technology that can drive everywhere in all cities in the US. So how can one actor collect the data in all cities in the US? If we share data, kind of standardize the algorithm, share data, then everyone can benefit and be in a situation in which in a relatively short amount of time, within a year or two, we can all have this this pillar of technology behind us. Okay, what are the business status we have here with the driving policy? As part of our alliance with BMW and Intel, we established a model of collaboration with BMW on driving policy, and the policy would be part of an architectural offering to the industry. With the partnership with Delphi, we also established a model of cooperation on driving policy with the Delphi's branch called Automatica. Okay, so this is in production. Our algorithms here are in production, in serious development, and we hope to expand this many more. Last part of my presentation is the progress on fully autonomous driving, L4, L5. So let's first define what it is. When we're talking about level 4, we're talking about urban and highway. In some cases, it's only urban for mobility on demand. The takeover request, again, is not instantaneous, and you require a high-definition map. When you're talking about sensor configuration, in camera sensing is not only forward-facing, you have a cocoon, it's 8 field of view, 8 cameras, long-range cameras around the car. There are front and side-facing LiDARs and a radar cocoon. So more sensing, more 360 degrees, and more redundancy. Not only front-facing redundancy, we have also redundancy over side and rear by having both laser scanners, radars, and cameras everywhere in terms of redundancy. So this is level 4. We established partnerships. The BMW, Intel, and Mobileye partnership back in July, and yesterday there was also a press conference talking about the progress, about launching 40 test vehicles this year. So the partnership includes 2 programs. One is level 3, what is called highly autonomous driving, and the other one is level 4, 5, what they call fully autonomous driving by 2000, and both of them are launching 2021. We'll start with 2 IQ4, and later will be replaced by an IQ5. Beyond computer vision that is residing on the IQ, the corporation will jointly develop the fusion and jointly develop the driving policy, the results of which will be deployed on an Intel system on chip. And the scalable architecture would be offered. So the idea here is inclusive, to bring as many affiliated partners inside this in order to share resources, to share costs, and make sure that we reach a standardization with a critical mass. The second partnership is the Delphi Mobileye partnership. It is similar in its scope and timing. What we see here is that Mobileye is responsible for the surround vision system and all the fusion on an IQ5 chip, all the policy and reinforcement learning. So Automatica would be doing the software algorithms for the trajectory planning. We will be doing the reinforcement learning for the negotiation skills, and road experience management. Our mapping is also part of the system. As I said at the beginning of my presentation, it's also demonstrated live in the test track. And the purpose of this partnership is to cater to OEMs that do not have the appetite to put this kind of investment. It is trying to emulate what is being done today in driving assist, where suppliers first build the technology and then go offer it to OEMs. This kind of thing doesn't exist today in autonomous driving. What we're trying to do here through an alliance of suppliers is to build the technology and then go offer it to car manufacturers, and then in a period of a year or 2 to customize it and launch it. Mm-hmm. So let me show you. So this is the camera setup, just the 8 camera setup. And then there is cocoon of radars and laser scanners around it. So let me show you some examples. So this is the camera sensing 360 degrees. So the green carpet is our free space. You see the 3-dimensional boxes around the vehicles, the 3-dimensional sensing of the vehicles, and of course traffic light, traffic signs, pedestrians. And you see this also from a wing camera and from a pillar camera in different, and also lane detection from 360-degree sensing. Let's have a look at, so there were many, many media reporters taking a test drive yesterday, and I found something on the web which is very nice, and in 1 minute explains everything. So let's run this.
CES, where I've just taken a ride in the latest version of Delphi's autonomous research vehicle. This is an Audi SQ5 that Delphi is fitted with radar, LiDAR, and what's new for this generation is a camera system from partner Mobileye. That means 9 cameras around the vehicle to give this car a better sense of its surroundings. During the drive on a set route, this car acted very naturally. It was aggressive enough, but safe enough. It felt like a human was behind the wheel. There's a display in the car that showed me what the car was seeing. I could see when it could see pedestrians, crosswalks, traffic lights. It really had a great sense of its surroundings. One thing that really impressed me is while we were in the left turn lane, another car cut in front of us, and the Delphi car behaved perfectly. Another time, we also went through a fairly long tunnel. The car lost its GPS connection, but still stayed on course. And one final thing that really impressed me is that this car uses crowdsourcing to determine its path down the road. It sees the path that similarly equipped cars have taken before it, and so it follows that path as well as lane lines. Now, this is still a research vehicle, but Delphi says this system could be ready for production around 2019, which means we could see it in a production car around 2020 or 2021. We'll see many more autonomous car technology demonstrations.
Okay, so and this is just the beginning. We announced the partnership back in end of August, so this is a result of 3 months of integration. 2017, there's much more to do. So this is a kind of summary of our partners for level 4. So we have Nissan and BMW, Audi we just mentioned, and we had 2 press releases in the last few days by Lucid Motors and NIO. These are non-traditional car makers, electric vehicle car makers, and this is level 4 setup, and 4 out of these 5 have RAM technology already committed. Okay, so we're talking about 10 production programs for autonomous driving, 5 level 3, 5 level 4. So let me just summarize. 2016 was a very good year. We had 12 design wins and production till 2026. 2016 also emerging partnerships with OEMs and supply base, with the BMW Intel partnership, the Delphi partnership, and tech EV OEMs like Lucid and NIO as partnerships. REM was the first live use of REM in this CES demo. We have acceptance by map makers like HERE and Zenrin. 2018 program launches are committed to include REM harvesting. An Asian OEM for level 3 launch will include the REM roadbook and localization in 2018. REM included in all the partnerships that I mentioned before. And the World Roadbook deal with many OEMs is ongoing and will be concluded quite soon. We have 10 serious developments, programs for autonomous driving. So we're not talking about research. This is production programs, 5 for level 3, 5 for level 4. And also the last slide here is that 2016 is the year where Mobileye began really executing a value expansion. If you look at Mobileye at the time of the IPO, August 2014, Mobileye was mainly focused on ADAS, monocular ADAS front-facing. If you look at Mobileye today, we're still heavily involved in ADAS monocular, but much beyond that. We're involved in mapping, we're involved in the driving policy, we're involved in multi-camera setups, the trifocal, the 8 FOV. So it is a completely different company than it was 2.5 years ago in terms of its value proposition. I'll end here and I'll take the floor for questions. Thank you.